In human languages, words constantly morph to express tense, plurality, and case. To a computer, raw unnormalized text presents an explosion of unique tokens that masks the underlying semantic truth. Consider words like investigators, analyzing, or transmissions. Each belongs to a vast linguistic web of structural deviations. Without consolidation, an algorithm treats these variations as entirely independent features, diluting its predictive statistical weight. To resolve this complexity, natural language processing offers two structural philosophies. On one hand, we have the fast, rule-driven approach of stemming. On the other, the deeply analytical, dictionary-backed process of lemmatization. Let's observe stemming in isolation. Stemmers operate blindly via cascading execution rules without understanding grammar. If we pass the token troubling into a common Porter stemmer, the engine matches a string suffix condition. It aggressively chops off the trailing characters, outputting TROUBL. Notice that it does not care if the remainder is a real dictionary entry. It merely searches for a structural common denominator. Now evaluate lemmatization. Instead of using computational string slashing tricks, it behaves like a clinical linguist if we feed it the highly irregular verb was. A stemmer would completely choke, leaving it unchanged or corrupted. The lemmatizer dynamically queries an extensive morphological vocabulary database, reviews the context, and transforms the irregular token perfectly back to its true infinitive canonical dictionary lemma. B. But why do we actually need to do this? Why not just leave the text exactly as the author wrote it? Let's build an intuition using a search engine. Suppose you are running a cooking blog, and a user searches for the term baked potatoes. In your database, you have a spectacular recipe titled How to Bake a Potato. If your search engine looks for an exact match, it compares bake with bake, and potatoes with potato. Because they don't match letter for letter, the search engine returns 0 results. Your user leaves hungry, and your website loses traffic. By introducing normalization, we collapse the search space. Baked and bake both reduce to the root form, as do potatoes and potato. Suddenly, an impossible exact match problem becomes a perfect conceptual match. In modern NLP, this drastically reduces our vocabulary size. Instead of forcing a machine learning model to learn separate mathematical meanings for tens of thousands of structural variations, we compress the vocabulary. This saves immense amounts of computer memory, speeds up training times, and helps algorithms recognize patterns they otherwise would have missed. Now that we know why we need them, let's pit them head to head to see exactly how they differ across accuracy, speed, and intelligence. The fundamental difference lies in context and vocabulary validation. Stemming operates blindly using heuristic rules. Because it operates on pure structure, it frequently suffers from two classic errors: overstemming and understemming. Overstemming happens when it chops too much off. Take the words universal, university, and universe. A stemmer might aggressively butcher them all down to UNI versus ERS. It has completely obliterated the massive difference in meaning between higher education and outer space. Lemmatization completely avoids this madness by utilizing a part-of-speech tag, or pause tag. It looks at how a word is being used in a sentence. Consider the word saw. If a stemmer sees saw, it leaves it as saw. But a lemmatizer asks, is this a noun, like a handsaw? Or is it a verb, as in I saw a movie? If it's a verb, it intelligently traces the word back to its true infinitive lemma. See This intelligence comes with a trade-off. Stemming is incredibly fast because it's just a set of simple string cuts. Lemmatization is computationally expensive because it has to read the whole sentence, calculate parts of speech, and look things up in a dictionary. Speed versus sophistication. Let's pull back the curtain and look at the actual engines running these systems. How do they perform these calculations under the hood? For stemming, developers rely on algorithmic rule sets. The most famous is the Porter stemmer. Designed way back in 1980, it applies conditional rules in sequential phases. For instance, a basic phase 1 rule looks like this. If a word ends in SSES, replace it with SS. Mapping caresses to caress. While the Porter stemmer is relatively gentle, the Lancaster stemmer is notoriously aggressive. It uses a much harsher, dynamic rule configuration that frequently leaves words entirely unrecognizable, though it is blisteringly fast. Lemmatization doesn't rely on blind truncation rules. Instead, it relies on complex lexical databases like WordNet. To find a lemma, the system sets up a mathematical lookup function that takes two arguments: the token itself, W, and its parsed part of speech tag, T. We can think of it as a function mapping. As you see, the algorithm explicitly links the precise linguistic shape with structural positional variables to extract a clean canonical lemma. If you pass the word meeting with a noun tag, the database maps it to the structural entity meeting, as in an event. But if you pass meeting with a verb tag, the mapping system identifies the root action meet. It requires an algorithmic tree search through structural language rules and exceptions lists to output the correct lemma. Now that you're an expert on how these two normalization pipelines function, where do you actually deploy them in the real world? Because of its raw execution speed, stemming is heavily favored in large-scale information retrieval pipelines and classic search. Indexing. When an engine needs to index billions of web pages every hour, it cannot afford the computational overhead of deep contextual analysis. It needs to chop, index, and move on. Conversely, lemmatization is mandatory whenever context, grammar, and semantic meaning are critical to the application's survival. Think about sentiment analysis. If a customer writes, "I am not liking this product. It worstens my experience," a crude stemmer might butcher worstens into something completely meaningless. A lemmatizer preserves the accurate semantic root bad or worse, allowing a sentiment classifier to accurately assign a negative score. You will also find lemmatization running inside chatbots, machine translation engines, and text summarization tools where maintaining valid language syntax matters. In summary, if you are dealing with massive volumes of text where raw speed is king and minor spelling errors don't matter, reach for stemming. If you are building intelligent, context-aware AI models where grammatical truth is non-negotiable, pay the computational cost and choose lemmatization. Let's look at how to implement this in Python. For a lightweight rule-based stemmer, we can use the NLTK library. For an industrial, context-aware lemmatizer, Spacy is our go-to solution. To initialize the Porter stemmer, we instantiate the class object and pass our target string through the .stem method. As you can see, passing studying drops out the raw shortened root stem, studi. Now let's spin up Spacy. We first load their standard English linguistic model dataset. When we parse a full sentence structure like, "The leaves are flying," Spacy dynamically runs taggers and parsing engines under the hood. Iterating over the text tokens yields clean, accurate dictionary lemmas. Leaf, bee, and fly.